Hello everyone, in this video I'll be talking about organic reactions and kinds of reactions, mechanisms, polar, nonpolar, bond dissociation energies and reaction profiles of alkanes, mostly hydrocarbons, in detail, like free radical reaction or halogenation reaction of alkanes in depth. So first we will discuss the types of reactions. For example, this is addition reaction where we add HBr across the double bond. This is the simplest alkene, that is ethene, and it contains 4 hydrogens and pi bond. Pi bond is rich in reactivity. So what happens is one of the carbon gets this hydrogen and another carbon gets the Br, and we prepare alkyl halides from the alkenes, and that is addition reaction. Why? Because we are adding across the double bond. HBr is being added across the double bond. Next type of reaction is elimination reaction. So elimination reaction is removal of some groups from the starting compound, from the substrate. For example, this is alkyl halide, and this is alpha carbon, and this is beta carbon. And the hydrogens that are attached to the beta carbon are called beta hydrogens. Let me pick the pointer. This is alpha carbon and this is beta carbon. So beta carbon contains hydrogen. Those hydrogens are called beta hydrogens. And this is a sodium hydroxide, which is a base, and it will help out the elimination reaction. What happens? This base deprotonates this hydrogen and the negative charge is generated, and this bond breaks in the favor of this carbon double bond carbon, and bromine acts as a leaving group. So we get NaBr and water as byproducts and alkene as products. So the take-home message from this reaction is that we can prepare alkyl halides from alkenes, and we also prepare alkenes from alkyl halides, vice versa, and by 2 different reactions. So addition reaction of hydrogen bromide across double bond gives you the alkyl halide, which is this one, and the elimination reaction of alkyl halide will give you the alkene. Let's discuss the another type of reaction, that is substitution reaction. One is polar and one is non-polar. So polar substitution, where polar groups are involved, and non-polar groups such as alkanes, like methane is a non-polar compound, is involved. That's what we call non-polar substitution, and this is called polar substitution. So this is a methyl bromide. It's a primary alkyl halide, and we have a nucleophile potassium cyanide. So what happens is cyanide acts as a nucleophile, and this is a carbon which is called electrophilic carbon, electrophilic center, and the negative charge on cyanide attacks on this carbon and the bromine leaves, and we will get the inversion of the product when the reaction is followed by SN2 mechanism, and we will have a nitriles as a product. So from alkyl halide we can prepare the nitriles, and that is called polar substitution reaction because bromine is more electronegative than the carbon. So bromine gets the partial negative charge and the carbon gets the partial positive charge. And this is a non-polar type of substitution, where we have a methane which reacts with Cl2 in the presence of sunlight, and we get CH3Cl plus HCl, and as the reaction progresses we replace all the hydrogens of this carbon is replaced with halogens, and the final product we get is carbon tetrachloride. Why this is non-polar substitution? Because the carbon is attached with 4 hydrogens, and the electronegativity difference between carbon and hydrogen is not much. There's no big difference between the electronegativity of carbon and hydrogen. Hence the bond between carbon and hydrogen is very non-polar in nature. That's why this reaction type is called non-polar substitution. Let's move on. Next type of reaction is a rearrangement reaction. So where one group rearranges to give the stable intermediate and give the products. For example, this is alkene. When acid is catalyzed, when acid is used as a catalyst, what happens is double bond is protonated and we generate a carbocation, and after that generation of carbocation the reaction rearranges to give you this product. So there are various name reaction rearrangement like Cartius rearrangement, Van Rib amide rearrangement, Bayer-Williger rearrangement, Fevrosky rearrangement. So it's kind of a detailed study of rearrangement reaction that I'll be discussing more in detail about next video, which when I will discuss exclusively about rearrangement reactions, and then you can understand in depth what is the rearrangement and what are the types of rearrangement and how many different functional groups can be synthesized using the rearrangement reactions. So these are some reactions that you students has to classify for me that what kind of reaction this is. For example, this is ethyl bromide, which is a primary alkyl halide which reacts with sodium cyanide and gives you the nitrile, ethyl nitrile. What kind of reaction it is? So I'm asking from the students, can you guys tell me the answer of the option A? Put your answer in the comments below in the video of this channel, and then I'll check the answers by following your comments in the YouTube channel video. Now next reaction is reaction of alcohol. This is cyclohexanol, which reacts in the presence of acid catalyst and gives you the alkene as a product and water as byproduct. So what kind of reaction this is? Next reaction is reaction of diene with the ene in the presence of heat. What kind of reaction this is? Think about some electrocyclic reaction. That is the hint I am giving you guys. Question number D is alkane, cyclohexane, which is a cycloalkane, and it reacts with NO2 in the presence of light, and it gives you the cyclohexane nitrocyclohexane, 1-nitrocyclohexane. And also the hint is reaction is taking place in the presence of light. So think about generation of free radicals, and the starting material is alkane. So these are the 4 questions that I am leaving you guys to answer me, that what kind of reaction it is. Is it a rearrangement? Is it an addition reaction? Is it a elimination? Is it a substitution? Is it a polar substitution, or is it a non-polar substitution? So you have to answer all of these 4 questions, and you can see these questions. I can wait for you guys to look at the questions. Okay, let's move on. There are some definitions. What is mechanism? So mechanism is a complete step-by-step of exactly which bonds break and which bonds form and in what order. That is called mechanism. What is thermodynamics? The study of the energy. So some reactions are thermodynamically favored and some reactions are kinetically favored. So in order to go in detail which reactions are thermodynamically favored and which reactions are kinetically favored, before going into that we should study the thermodynamics or the definition of thermodynamics and kinetics in the light of organic chemistry, not in the physical chemistry or physics, So the study of the energy changes that occur in chemical transformations. This allows for comparison of stability of reactants and products. That is called thermodynamics. And kinetics is the study of reaction rates, determining which products are formed most rapidly. One can predict how the rate will change with changing conditions. Next is reaction profile. That is this reaction profile is for exothermic reactions. So this is the reaction coordinate on the x-axis and energy is on the y-axis. And this is the rate equation. Kr A power A and B power B. So these are the reactants. AB react together to give the product CD, and this is the activation energy barrier required, and this reaction undergoes some sort of a transition state which is indicated with this sign. This is the delta H, heat of formation, and as you can see the reactants are higher in energy and products are lower in energy, and this reaction profile is for exothermic reaction. And what is the second order reaction? So for example, this is alkyl halide which reacts with a base. Nucleophilic substitution reaction takes place. So in order to write the rate expression, rate is equals to K. So this is the starting material and this is the real nucleophile. Second order rate kinetics is written in this way. First order kinetics is written in this way. This is the SN1 reaction. So this was the SN2 which is a second order reaction, and this is a SN1 which is a first order reaction. So first order rate kinetics. So the starting material is tertiary alkyl halide which reacts with water. We still get the substituted product alcohol, but the rate expression is just involves the starting material, that is the alkyl halide. Hence this is called first order rate kinetics. Now the bond breaking nonpolar and polar. So this is there is a bond between A and B, and this bond is due to the presence of two electrons. One is from the A and the one is from the B. So two electrons are responsible for the bond making in the A and B. So the one electron is shifted towards A and one electron shifts towards B. So we get the A radical and B radical. This is called homolytic bond breaking radical. One electron stays with each fragment. This is A and B. So this bond breaks in the favor of B, and B gets the negative charge and A gets the positive charge. So this is a heterolytic bond breaking. So this is polar. Two electrons stay with one fragment. As you can see, these two fragments are polar. One is positive and one is negative. So and positive is called cation and negative is called anion, and these two are called radicals. So in homolytic bond cleavage, the radicals are generated. In heterolytic bond cleavage, and cations or anions are generated. This is a non-polar reaction, involves free radicals. So radical which is formed radical reactant, radical which reacts with A and B compound. So the one electron from the radical reacts with the one electron of the product, and one electron goes to the B. So the substitution product is this, and the radical product is this unpaired electron. So free radicals are neutral but electron deficient. Okay, like carbocations are positive, anions are negative, but free radicals are neutral and they are electron deficient. This is the Lewis structure of chloride, which contains a free radical electron. This is the Lewis structure of bromide. This is the Lewis structure of hydroxide. This is the Lewis structure of methyl. The Lewis structure of ethyl radical. As you can see, this electron is a radical. This is a radical, free radical. As you can see that the full octet is not complete in the Lewis structure, and we can simply write this structure as Cl dot, and this is radical, Br dot, OH dot, methyl radical, ethyl radical. Free radical of reaction of chlorination. So this is methane and this is chlorine. It reacts with light and we get chloromethane as a first product. So experimental evidence helps to determine mechanism. Chlorination does not occur at room temperature in the dark. The most effective wavelength of light is blue, that is strongly absorbed by Cl2 gas. The light initiated reaction has a high quantum yield. Many molecules of products are formed from each photon of light. So this is Cl, and the electrons are shared between two Cl, and due to the light the cleavage happens, and the one electron goes to one chloride and another to the another, and we generate the chloride radicals. And now this chloride free radical, this is a first step, propagation step. This was the initiation step where initiation took place by the formation of radicals. This is the propagation step where this chloride free radical reacts with this radical to give methyl radical, and then in second propagation step takes place, and we get the methyl radical reacts with chlorine molecule to generate the chloromethane, and the termination reaction of any two radicals. So this reaction can be terminated at methyl chloride and we get the Cl, or we can get this reaction of this methyl with methyl and we get ethane as a product. And this radical collides with wall, and this chloride collides with wall. So the initiation radicals are formed. Light supplies the energy to split a chlorine molecule. So this is a chlorine which splits in the presence of light to give two chloride radicals. And next step is propagation. A radical reacts to generate another radical. Step 1, a chlorine radical abstracts a hydrogen to generate an alkyl radical. So this is methyl, which reacts with chloride radical to give you the methyl radical. And step 2, the alkyl radical reacts with Cl2 to generate the product and a chloride and the chlorine radical. This chloride reacts with this one, and this is chloromethane, and continues the chain. Enthalpy of reaction delta H measures difference in the strength of bonds broken and bonds formed. Bond dissociation energy. So this is a bond that is formed between two A A and B. So bond dissociation energy will be required to dissociate the two bonds and generate the free radicals. Here are the here is the table. And this is the table that will guide you to the bond dissociation enthalpies and homolytic cleavage. So I would like you guys to have a look on this table. I will wait and you can note down this table. And as you can see, this is the detailed bond studies of the bond lengths and bond dissociation energies. First one is the halide bonds, HX. Second one is methyl. Third one is bonds to primary carbons. This is bond to secondary carbons. This is bond to tertiary carbons. And this is other hydrogen. And this is CC bond. This is a bond dissociation energy in kilojoule. And this one is a bond dissociation energy in kilocalorie per mole. And this is a bond dissociation energy in kilojoule per mole. And this is a bond dissociation energy in the So this one is bond dissociation in enthalpy in kilojoule per mole, and this one is bond dissociation energy in kilocalorie. This is the formula, that is the heat of formation, the bonds broken minus bonds formed. So overall reaction is the reaction of methane with chloride, and the bond is found between carbon and chlorine, and the bond is found between carbon and chlorine and hydrogen. The bond is broken between carbon and hydrogen, and the bond is broken between chlorine and chlorine. So bonds broken chlorine requires energy of 242 kilojoule, and bonds that is being broken between carbon and hydrogen requires energy of 435. So the net bond energy broken is 677. And this is bond formed. This is the HCl, which is the bond breaking energy, that is 431. This is methyl chloride, which has the energy of 351 kilojoule per mole, and the total energy is minus 72 kilojoule, which is involved in bond formation. So delta H reaction is minus 105 kilojoule per mole. The first propagation step requires 4 kilojoule per mole energy, and 435 energy is required to break the bond between carbon and hydrogen, and the methyl radical is formed, and the H hydrogen, and the bond between HCl, bond between hydrogen and carbon, is involves minus 430 minus 431 kilojoule per mole. And second step is a propagation step, which requires minus 109 kilojoule per mole, and this is a radical formation. Radical is formed, methyl radical, which further reacts with chloride, and this is the bond making between carbon and chlorine, and it requires plus 442 to break the bond between chlorine and chlorine, and the minus 351 energy is required to make the bond between carbon and chlorine. Now the question is, this is the light Cl2, two chlorides are reactant. B, Cl radical reacts with methane to give methyl radical. Then methyl radical reacts with Cl2 to give you the methyl chloride. So this is the mechanism of free radical. Why not this mechanism? First, formation of two chlorides, then chloride reacts with methane to give you methyl chloride, and then H radical reacts with Cl2 to give you the HCl and chloride radical. Why not this mechanism? Why this mechanism is followed? So if you see here, these are the primary hydrogens, these are the secondary hydrogens, and these are the tertiary hydrogens. Why? Because this carbon is connected with one R group, and this carbon is connected with two R groups, and this carbon is connected with three R groups, 1, 2, and 3. Or you can say this carbon contains 3 hydrogens, that's why it's called primary carbon or primary hydrogens. This carbon contains 2 hydrogens, that's why it's called secondary hydrogen, and this carbon contains 1 hydrogen, that's why it's called tertiary. So 6 primary hydrogens are present here, which reacts with Cl2, and this is primary chloride is formed. Relative reactivity 40%, 6 hydrogens, so 6.67% per hydrogen radical formation is chances. Whereas in 2 secondary hydrogens, where these are the 2 secondary hydrogens indicated, so Cl2 reacts with in the presence of light replacement of this 1 hydrogen with Cl. Secondary chloride, there is a 60% chances of 2 hydrogens, so 30% per 1 hydrogen chances is there. So the secondary hydrogen are 30 divided by 6.6, so 4.5 times as reactive as the 1 degree hydrogen. So secondary are more reactive. Chlorination of propane, as you can see, the first reaction is the first step is initiation, splitting of the chlorine molecule Cl2 plus H nu to give you the chloride radical. Second step is a propagation step, abstraction, removal of a primary or secondary hydrogen. So these are the all primary hydrogens, and what happens is this CH3 loses its 1 hydrogen to give you the primary radical, which rearranges to form secondary radical, and HCl. Second step is reaction with chlorine to form the alkyl chloride. This reacts the primary chloride, which is in the 40% yield, and whereas the rearranged radicals, which is secondary radical, reacts Cl2 to give you secondary chloride, 2-chloropropane with 60% yield. Why? Because secondary free radicals are more reactive than the primary. So reactivity of primary hydrogen is 6.7, reactivity of secondary is 30, rate of 2 hydrogen secondary abstraction is 4.5 higher than the primary one. Formation of a methyl radical, so bond dissociation enthalpy is involved 435 kilojoule, and formation of a primary formation of a secondary radical is that involves 397 kilojoule, and formation of tertiary radical involves heat of formation of 381 kilojoule per mole at 91 kilocalorie. So this is the reaction coordinate, and this is the energy profile. So this is the propane which reacts with the chloride radical, and this is the activation energy barrier for 1 degree hydrogen, and this is the activation energy for barrier for secondary hydrogen, and this is the difference in activation energy is about 4 kilojoule between 1 degree and 2 degree. This is the 1 degree radical, and this is the 2 degree radical. The energy difference between primary and secondary radical is 13 kilojoule per kilojoule. Chlorination of methyl propane. First, this radical is formed, which rearranges to give you the tertiary radical. This is a major product in 62% with tertiary. It's a primary, and this is the minor product, which is 38%. Tertiary hydrogens removed 5.5 times more radially than primary hydrogens in chlorination reactions. So fraction of primary 9.0 plus 5.5 equal to 62%. Fraction of tertiary 5.5 divided by 9.5 plus 5.5 equal to 38%. Tertiary radicals are easiest to form. Formation of a methyl radical. So methane reacts to give you the methyl hydrogen radical and methyl radical. This is the bond dissociation energy, that is 104 kilocalorie per mole and 435 kilojoule, and this is the formation of a primary radical. This is propane, which forms the primary radical, this one, and energy released is 98 kilocalorie. And the formation of secondary 2 degree radical, this is a propane, and this is the formation of radical, and this is the formation of tertiary radical, and it just involves 91. So as you can see from the energy, so the highest energy is bond dissociation energy is required to generate radical from the primary. Second highest energy required radical from the primary radical is again 98, and from a secondary is 95, and from tertiary is the lowest, that is 91. So this is the difference of bond dissociation energy that is required usually to generate the radical from different type of alkyls, so primary, secondary, or tertiary. Here is the stability of free radicals. So tertiary radical is more stable than the secondary. Secondary is more stable than primary. Primary is more stable than the methyl radical. This is the bromination reaction energy profile. We have a reaction coordinate on x-axis, energy on the y-axis. This is propane. This is a bromine radical. So bromination is an endothermic reaction, transition state close to products, large energy difference in activation energy. So reactants are lower in energy and products are higher in energy. So the about 2.5 kilocalorie difference in activation energy. As you can see, for the primary one is this, primary radical formation is this, and this is a secondary radical formation. This one is a primary radical and this is a secondary radical. As you can see, the secondary radical is radially formed than the primary radical. That's the difference of energy, activation energy between primary and secondary radical formation. So this is the energy profile for the endothermic bromination reaction. So the bromination is very selective. For example, this is bromine. This is a propane which reacts with bromine Br2 in the presence of sunlight HNu at 125 degrees centigrade, and we generate a propyl bromide which is 3%, and the secondary bromide is generated 97%. So the secondary radical reacts faster with the bromine radical. So 6 primary hydrogens, 3% divided by 6, so 0.5% per hydrogen relative reactivity in case of primary radicals. So in case of 2 secondary radicals, the reactivity is 97% divided by 2, that is equals to 48.5% per hydrogen. The 2 degree hydrogens are 48.5 divided by 0.5 is equals to 97 times as reactive as the 1 degree hydrogens. So this is the reaction coordinate. Now this is the energy profile. This is the propane and this is a bromine radical. Here is the energy, activation energy for 1 degree, and here is the activation energy for 2 degree. This is a 2 degree radical, that is a propane radical, and this is a propane radical or primary 1 radical. Difference in activation energy over 9 kilojoule per mole between these two in case of bromination of the propane. So due to the large difference between two different radicals, it causes the delay in reaction of that decreases the yield for the primary alkyl alkanes, primary free radical than the secondary one. So secondary one has the higher rate and than the primary one. So that's the primary secondary radical. RDS is in bromination is highly endothermic. So reactants close in a structure, transition state, that is a transition state that is in the bromination close in energy products, and this one is in reactants close in energy. This is a chlorination energy profile and this is a bromination energy profile. As you can see, there's difference of energy profiles for chlorination and bromination. So for bromination, reactants are lower in energy. For chlorination, reactants are higher in energy. The second difference is in bromination, products are higher in energy, whereas in chlorination, reactants are lower in energy. And as you can see, there is a transition state which is close in structure to products, and the transition state energy is closer to the product. So but here in transition state is similar to the reactants and closer to energy of the reactants and far from the product. So that is a big difference between bromination and chlorination of reactions which involve the radical formation or the free radical reaction of chlorination bromation on the alkanes. Consider the free radical monochlorination of 2,2,5-trimethylhexane. Draw all of the unique products, ignore stereoisomers, use zigzag structures please, and predict the ratio or percentage composition of the products. The relative reactivity of hydrogen abstraction in a chlorination reaction: 1 degree, 2 degree, 3 degree is 1:4.5 is to 5.5. Chlorofluorocarbons and the depletion of ozone. So this is the ozone which reacts with sunlight to give you the oxygen and oxygen radical. This is a chlorofluorocarbon. This is CFC. Chloro, this is chlorine, fluoro because of the fluorines, and carbon. So it reacts with ultraviolet light to generate the chlorofluororadical, and this chloride radical reacts with ozone to generate the ClO radical, and then this ClO radical reacts with oxygen radical to give you the Cl radical and O2, and net reaction is depletion of the ozone. This reaction explains how ozone layer is destroyed by sunlight, and this reaction is also explained through the free radical chain reaction mechanism. So generation of radicals takes place, hence the O3 is converted into O2, and hence this is how ozone layer is destroyed in the sky, which protects the harmful rays of the sun. If there's no ozone layer, then there are high chances of cancer, and the skin cancer particularly, because the ozone layer protects us from the harmful rays, radiations of the sunlight, and otherwise the harmful rays will penetrate through our skin and will cause cancer. And this is the mechanism that how ozone layer is destroyed by the chlorofluorocarbons, and they generate free radical, and then they destroy the O3 into O2. Now the discussion that we discussed so far was related to non-polar nucleophilic substitution. So there is a more to it, polar reactions which involve electrophiles and nucleophiles and electrophiles. So electrons usually flow from one of these nucleophiles, and electrons usually flow to one of these electrophiles. So oxygen is a nucleophile which gives electron to the electrophile. Nitrogen is a nucleophile which gives electron to the electrophile. Carbon, having a negative charge, will act as a nucleophile, and that will donate electrons to the electrophile. Double bond in alkene is rich in electron density, which will donate electrons to the electrophile. This is how nucleophiles donate electron density to the electrophiles. Or in this case, nucleophile is attacking on the electrophilic center, nucleophile is attacking on the carbon halogen bond, nucleophile is picking proton from this hydrogen, and nucleophile is attacking at the carbonyl group, and the bond between carbon double bond oxygen breaks in the favor of oxygen. So these are the very simple things that I'm explaining to you that will help you to understand the complex reactions. So the polar reaction involves the nucleophile and the electrophile. So the nucleophile rich in electron attacks on the electrophile which contains a positive charge to prepare AB molecule. Whereas in the free radical reaction, so the B and A are free radicals, so they combine through radical formation to give you the AB. Nucleophiles are bases, electrophiles are acids. Negatively charged atom is a nucleophile, and the positively charged atom is electrophile. So oxygen having a negative charge will act as a nucleophile, and HBr, that is the electronegativity difference between in HBr is Br contains a partial negative charge and hydrogen contains the partial positive charge. So the bond breaks between HBr and Br gets the negative charge. The molecule is neutral, that is methanol. Addition of HBr to ethylene is also the nucleophilic substitution addition reaction. So the alkene attacks, the pi bond attacks on the HBr, picks proton first, and then bromine attacks on the carbon to give you the ethyl bromide. Here is the rate equation. Reactions often go through intermediates. So this is the first step which is involved the formation of a carbocation in the addition reaction of HBr to the alkene. This hydrogen already has 2 electrons. When another electron pair moves to the hydrogen from the double bond, the electron pair in the HBr bond must leave. Here is the transition state of the alkene with the HBr. Here is the energy profile of the bromine addition of HBr to the alkene. So reactants are lower in energy, products are higher in energy. There is the transition state which is closely resembles with the product. This is the carbocation product, and this is the intermediate. This is activation energy delta G, and we have a y-axis energy profile, and on the x-axis we have the reaction coordinate. Addition reaction is a two-step reaction. So addition of alkene to the addition of HBr to the alkene. First is a intermediate formation, that is a carbocation, and in the next step bromine attacks on the positive charge to give you the alkyl halide. Here is the full reaction energy diagram or energy profile for the formation of the alkyl ethyl bromide from the ethene. So this is ethene which reacts with HBr, and this is the transition state. This is the formation of carbocation, intermediate, second transition state, and gives you the products. So products are in lower energy and reactants are higher in energy. How many mechanistic steps, how many intermediates, how many transition states, which step is rate determining? Over to you guys. Answer all of these 4 questions in the comments. I'll leave the video here on this question. So you have this energy profile diagram. All you need to do is to answer my question based on the study that we have done before. And if you find any difficulty in answering these 4 questions related to this energy diagram, so you have to label that this is a reactant, this is a product, this is the energy, this is what is the transition state, which is transition. So you have to label and answer these 4 questions based on this video lecture. You can pause this video and revise again the concepts anytime. And thank you all for listening, and take care. Bye.